Let's start.
Hello everybody. Welcome to the special functions and number theory seminar. Today's talk is by Atul Dixit on the Rogers-Ramanujan dissection of a theta function. Yes, go ahead.
Thank you, Gaurav. Thank you all for coming to this talk. So this is joint work with Gaurav Kumar. So it concerns an identity on page 27 of Ramanujan's Lost Notebook. I mean, there have been thousands of identities of Ramanujan, many of them of which, or most of them rather, are very captivating. And not only that they are captivating, they also contain a lot of information, a lot of applications. So here is one such about which I'll be talking. So let me just start with that identity. So here A is any non-zero complex number and B is any complex number. So you see, we are summing product of two infinite series. I mean, two products, one each consisting of two infinite series. And then we are summing that. And the addition is equal to a theta function divided by a q product minus 1 minus b times this particular series. So apparently it just looks like something pretty fancy, but I'll try to convince you that it's also very, very important identity. Although it's not among the 10 fascinating identities that Andrews and Berndt listed in their nice article in Notices of AMS a few years ago. But I'll try to convince you that this is also a very important identity. So let's first try to, I hope everybody is familiar with the Q notation. So Q sub n will be 1 minus Q square, so on up to 1 minus Q to the power n factors. So BQ sub m will be 1 minus BQ, so on up to 1 minus BQ to the power m. Okay, what I'm going to do is I'm going to let A and B both as 1. And then I'm going to replace Q by Q raised to 4. So when I let A and B be both 1, people will easily identify what this particular sum is, Q to the m square upon Q sub m. It's the Rogers-Ramanujan function, the first Rogers-Ramanujan function, G of Q, as it is denoted. And I'm going to replace Q by Q raised to 4. So this is going to be G of Q to the power 4. On this side, what I'm going to get is Q to the power n square upon Q raised to 4, Q raised to 4 sub n. But if I multiply throughout by minus Q square sub infinity, then there is an identity of Rogers, which gives us back, see, this was the sum that we get from here. And if I multiply by minus Q square sub infinity, I'm going to get back Q, G of Q. So this becomes G of Q in this process, and this becomes G of Q to the power 4. Similarly, this becomes H of Q, the second Rogers-Ramanujan function, and this becomes H of Q to the power 4. Of course, B is equal to 1, so this thing just vanishes. And what you get from here is this modular relation involving the Rogers-Ramanujan functions. On the other side here, phi of Q is the Jacobi theta function. So this itself is among the very celebrated identities of Ramanujan. This is a modular relation because you are having Q and Q to the power 4 linked together by means of this identity. Now, regarding this identity, Andrews has this to say. If you take the Narosa edition of Ramanujan's Lost Notebook, in the preface, he says this. This sort of identity has always appeared to me to lie totally within the realms of modular functions and to be completely resistant to Q-series generalization. One of the greatest shocks I got from the Lost Notebook was the following assertion. What was that assertion? That was basically that this particular thing can be generalized with the parameters A and B. Now, it's not very often that something like this happens. So how did Ramanujan come up with this identity? That is something we are going to answer along the way. But there are also further other things that I want to say. Now, this was what we did. So this appears in Andrews's monograph, Partitions Yesterday and Today. This is from, I guess, 1979. So if you see this particular thing, we put A and B as 1. Now, if I put A and B as -1, and then again replace Q by Q raised to 4, and you multiply by minus Q square sub infinity, again use the two identities of Rogers, this is what we get. G of Q and H of Q, again the two Rogers-Ramanujan functions are there. And here we have the fifth order Mach theta functions coming in, F0 and F1. And now the right-hand side, this thing doesn't vanish. Note that there is a 1 minus b. So with b equal to -1, this becomes 2. Nevertheless, you have an identity connecting these four important functions about which Andrews says that nothing like this appears in any of the literature on Mach theta functions. And this is back in 1979. Even to this day, to the best of my knowledge, this is a true statement. There is no identity connecting these four functions or functions of this type. Is that it? No, there is a lot more in it. By the way, Andrews calls this as a generalized modular relation because its special case is this modular relation involving G q to the power 4, H q to the power 4. How did Andrews prove this identity? He observed the left-hand side and the right-hand side as a Lorentz series Lorentz series in A, and then he showed that the coefficients of this A to the power capital N are the same on both sides, but that requires knowing the identity in advance. So one of the goals of this work is to show that a natural proof can be obtained, and in the course of it, we also generalize this identity. So now, what is the generalization that one can get? To answer this, let us first look at one question which is there on page 26 of the last notebook. So Ramanujan just writes this product and as q tends to 1. So what is the asymptotic behavior? That's what he is asking, as q tends to 1. But if you notice, when s is equal to 2, this particular product was the first term on the left-hand side of the identity in blue, which is on the page 27 of the last notebook. So if you put s is equal to 2, this is q to the n square by 4, that's here. And of course, with b equal to 1. And then this one gives you 2 upon 2. So it is a to the minus 2 n q to the n square upon q sub n, which is what is here with b equal to 1. Okay, so you actually see that Ramanujan is now looking at this and further generalizing it, although he doesn't have a b in there, but he has a parameter s. And he's asking what is the asymptotic behavior. We'll come back to this, the asymptotic analysis. But one thing that you find in part 2 of Ramanujan's last notebook by Andrews and Berndt is that Ramanujan provides no indication either why this is of interest for arbitrary S or what the asymptotics should be. So among other things, in our paper, we show that that product of the two functions as q tends to 1 from within the unit disk, it behaves in this way. Note that there is no special function in here. Everything is quite elementary, like pi square by 6, s over 2 log square a, and then -1 by log q. But the very fact that the special case of this left-hand side, when s is equal to 2, is a part of a identity which contains in it the modular relations for the Rogers-Ramanujan identities, the relation for fifth order Mach theta functions and the Rogers-Ramanujan functions, suggests that one should probably look at a generalization of that identity of Ramanujan with a general parameter S. And that is what is the main result of our paper. So now you see, you have, instead of q to the power n square by 4, q to the power n square by 2s. Now one may say that, okay, you just replace your q appropriately here. Why does it need to have in Ramanujan's identity itself, there was q to the n square by 4. You make it in such a way by replacing q by q to appropriate power that you get q to the n square by 2s. What's the big deal in it? But the big deal is that this also changes them. There is a bq sub m and q sub n in Ramanujan's identity, and that is going to change. Now, if you want to keep it the same as what occurs in the Rogers-Ramanujan functions, then what do you get as the representation for this particular theta function, or rather this right-hand side? And that is, instead of having two products summed, you have to have S products summed, each product consisting of two infinite series. And there is this number J, which is 0 when K is equal to 0 and is 1 otherwise. For all values of K from 1 to S minus 1, we'll take J to be 1. This will be throughout the talk. Whenever you see J, J has this meaning. Now, there are many formulas in the literature for theta functions. You can either represent a theta function to some power as a theta function times some Q series, which is something which comes from in root lattices. For example, Ramanujan's circular summation of theta functions. Or you have a theta function represented as a finite sum of products of theta functions. That is the famous Schroeder's formula. So this is a new kind of summation. This is representing a theta function in terms of sum of products of generalized Rogers-Ramanujan functions. And if I have b equal to 1, I mean, by generalized Rogers-Ramanujan functions, I mean not just a to the n, q to the n square by q sub n. That is also something which is called as a generalized Rogers-Ramanujan function. But here we are allowing here this exponent of q to be a quadratic in n divided by s. And in the denominator, we are allowing bq sub n and then a to the power n. So this series is what I'll call as a generalized Rogers-Ramanujan function. And then, sorry, what I want to say is that how do you write a theta function in terms of sum of products of these generalized Rogers-Ramanujan functions? So this is somewhat similar to Schroeder's formula, where a theta function is written as sum of products of theta functions. But here it is more involved because it's sum of products of Rogers-Ramanujan functions or generalized Rogers-Ramanujan functions. Now, how do we prove our identity? I'm not going to go over the proof because it's quite long, but let me explain the ingredients behind it. So in fact, we obtain corresponding representations for partial theta functions. So remember, the right-hand side here was minus infinity to infinity, but we have a representation for the partial theta function n equal to 1 to infinity as sum of products of two series, one of which is the generalized Rogers-Ramanujan function, and another is the tail of the generalized Rogers-Ramanujan function. On the other hand, if you are looking for an identity for minus infinity to 0, you get the first part, not the tail. N from 0 to Sm plus k. In the previous identity, it was n from Sm plus k plus 1 to infinity. And so when you add the two sides, on the right-hand side, you get the full theta function minus infinity to infinity. So actually, the identity holds at the level of partial theta functions also. This identity is not so difficult to obtain, but this one really takes a lot of effort. Anyway, I'll skip the proof, but I want to say what you can get out of this identity. So again, this is the generalization of Ramanujan's identity from page 27 of the Lost Notebook. And this is what we call as Rogers-Ramanujan dissection of a theta function when b is equal to 1. When b is equal to 1, this is not there. So there is essentially only the theta function. I mean, there is a product also that comes out 1 upon q sub infinity because b is 1. But we incorporate that product in the definition and we call this left-hand side as the Rogers-Ramanujan dissection of this theta function. Okay. So clearly one can very easily obtain Ramanujan's result by just putting s is equal to 2 in this. Now we have s as any natural number, right? So if I take s is equal to 1, sorry. If I take s is equal to 1, so Ramanujan's case is s is equal to 2 of our identity. Sorry, there is a phone call which is there. So if I go back and put s is equal to 1, there won't be sum of products. There will be only product of two series because s is 1. So k is just 0. K is 0, so j is also 0. So we don't see. So it's just product of two functions of this sort. On the right-hand side, you have a theta function and you have this. Can anybody recognize what this is? At least in the special case, if I put b equal to 1, This is nothing but the Jacobi triple product identity. Because when I put B is equal to 1 here, by Euler's theorem, this will turn out to be a Q product. And this will turn out to be a Q product. And if you replace Q by Q square, then this is the theta function f of A comma B with B appropriately specialized. So this is the third Q product. These two are the two ones, and this is the third one, giving us the Jacobi triple product identity. So I talked with Professor Andrews about this, and he said that it doesn't look like this has been. I mean, I asked him if he had seen something of this sort already in the literature, and it appears that this is new. So it's a new generalization of the Jacobi triple product identity that one can get. S is equal to 2 is Ramanujan's identity. What about S greater than 2? So if I put S is equal to 3, then I'm going to get K is equal to 0, 1, 2. So I'm having sum of products of three such things equal to this theta function divided by BQ sub infinity minus this. So I have a to the power n, q to the n square over 6. And now the natural question that comes up in our mind is that, does there exist an analog of the modular relation between G and H that we have here? So this is for S is equal to 2 when you put A and B both as 1. If I'm putting A and B both as 1 in here, do I get this self-similarity sort of thing, which is a modular relation? And it appears to us that it is very, very unlikely that such a self-similarity is obtained for S greater than 2. See, the key ingredient in getting this self-similarity was this identity of Rogers. So this, when you multiply by minus q square sub infinity, again gave us G of Q. And on the other side, there was G of Q to the power 4 because you had replaced Q by Q raised to 4. But it is unlikely that analogs of Rogers identities exist for S greater than 2. And let me try to convince, or at least try to explain what our thought process is. There is a generalization of this by David Brosseau. So remember that this is q to the power n square upon q sub n summed. Now here is q to the power n square upon q sub n times a to the power n. So very easily one can see that if I put a is equal to 1, this becomes g of q. Here I get this minus q square sub infinity. If I put a as 1, here I get q raised to 4 sub n. So this generalizes Rogers' first identity. But Brosseau, this can still be conceived at S is equal to 2 level, right? But if you want to go for S natural number, even though this remains as a single sum, this becomes a multi-sum. Note that if I put S is equal to 2, I get m square minus m plus m, which is this q to the power m square, a to the power m upon q sub m. So I do get this side. But on the other side, when I put S is equal to 2, then there is only one sum over n1. Capital N is also n1. And what I get is this sum. But for S greater than 2, for S is equal to 3 onwards, I'm going to get double sum, triple sums, and so on. So getting something in terms of a single sum, infinite sum, is very, very unlikely. But I'll also give some more convincing argument after I discuss the asymptotic analysis of Ramanujan's identity. Anyway, so in our general identity, when S was equal to 1 and I took A and B both to be equal to 1, I was able to get Jacobi triple product identity, right? If I put A and B both to be equal to minus 1, then I get this relation of Ramanujan between third order Mach theta functions. If I don't put B is equal to 1, I have the parameter B also, then this actually gives what is called as a relation between two generalized third order Mach theta functions of Andrews. Okay, so at every stage, even when S is equal to 1, you are actually getting new identities or well-known identities. But what I can do is, remember you have the theta function on the right-hand side. You can kill that theta function because you have this result, which can be established by just Q series manipulation or by using Jacobi triple product identity very easily. So I put A equal to -1, and then I appropriately specialize Q so that I kill the theta function, and what I get is just this part. There was a theta function in front divided by BQ sub infinity, and then this part, right? So I have killed the theta function using this simple identity. So I have this representation. What do I get when I put S is equal to 2? If I put S is equal to 2, there is an identity which involves 4 Q series, 3 of which are not studied. And the fourth one has appeared in Ramanujan's work, namely this particular series. Summation Q to the n plus 1 by 2 divided by Q square sub n. For this series, Ramanujan gives 4 identities, 2 of which are very easy to prove, and 2 of which are extremely hard to prove. So Andrews first proved them in his paper in Advances in Math, where he linked them to some objects in partition theory called stacks. But the proofs are very intricate. They use Bailey's 10 phi 9 summations and a lot of other ingenious arguments. Later on, 2 Indian mathematicians, Arun Verma and V.K. Jain, they generalized Ramanujan's identity, both these identities, which were difficult, but there has been no citation to that until this particular work, which is submitted, where we found that, oh, he has generalized it. Anyway, so only this identity seems to have been studied, though. Just a moment. Let me just. Yeah. So what is so important about these 4 functions? I mean, just by appearance, they look quite simple, but that's no longer a case in Q series. If you just change n to n plus 1, the nature changes. Something that was modular may become mock modular, or even resistant to any of these theories of modular forms, and it may be something just which we represent as basic hypergeometric series. So something like that can happen. But this particular one is quite important. It has been called one of the Q analogs of Airy function. Airy function, a special function which is well known. And it also arises as a hypergeometric solution of a Q-Pine-Levi equation, this particular series. There has been some work of Japanese mathematicians like Kajiwara on this, as well as by Murad Ismail. So while we were not able to simplify this any further, because none of these 3 Q series seem to have been studied before, we were able to get a congruence from them. And one of the 3 series was was eliminated, and what we got was a congruence modulo 2. So the sum over n, if you see, like this one, which is just changing the Ramanujan's function by replacing the plus in here by a minus, you get something which has been listed in OEIS, but it hasn't turned up in any of the papers because there are no references to it. It's just that somebody thought that, okay, instead of n plus 1 by 2, what if I take n minus 1 by 2? And they do have some description in terms of partitions, but that's it. That's where it lays. But these two do not seem to have been studied before either. Okay. Remember, I annihilated the theta function by means of a special choice. A was -1 and Q with an appropriate power. And then I had something involving 1 minus B on the right-hand side. I put B equal to 1. And I completely killed the right-hand side to get something like a system of equations that you can see when you sum, when you sum the products, you're going to get 0. This looks quite surprising. Let us try to see what we get when S is equal to 1. So when S is equal to 1, of course, there is going to be only one such product of 2 series. And this turns out to be very simple. rather very trivial, because what is this? If I had here z, that would be minus z sub infinity. So with minus 1, I'll get 1 sub infinity. So that kills this term. This term becomes 0, so everything becomes 0. But what do we get when s is equal to 2? For s is equal to 2, this is the identity. And this identity can actually be proven by using an identity of Mackintosh, Richard Mackintosh. In 1995, he conjectured this identity. Here, mu is a natural number. Later on, he, as well as Andrews independently, they proved using difference equations. But see, one has to resort to difference equations because mu is not a real parameter. Mu is just a natural number. So if you use this identity twice with mu being 0 and mu being 1, and then combine the two, then you can get the identity on the previous page. That is this one, which was the s is equal to 2 case of this identity. But for higher s, this seems to be new. So now you are getting sums or differences of these products being equal to 0. And that's quite surprising. That must mean something. There must be some explanation to this. Why do we get 0? How do we prove this? I already told you that we actually get corresponding identities for partial theta functions, and then we add the two. So one of them has the tail of an infinite series. One of them has the initial portion of the same infinite series. And when we put them, then we get the generalized Rogers-Ramanujan function. Along with that, what we need is the Durfee square analysis of this particular function. Okay, so if I just look at this particular thing and equate with this, that is already done by Andrews in his monograph. Even this identity for s is equal to 2 has been proved by Andrews. And is actually an identity of Ramanujan, which Andrews proved using Durfee square analysis. So he wrote the Ferret's diagram of a partition, and he considered not Durfee square, I should say Durfee rectangle analysis. So what he considers in his case is 1 cross 2 Durfee rectangle, and when s is equal to 2. And then he analyzes the partitions. So one of the sums you get from one particular analysis, and there is a further thing that we would be missing if we don't take all of the partitions into consideration. So this turns out to be sum of 2 such infinite sums. But in general, one needs a 1 cross s Durfee rectangle to be considered, and then one does a partition theoretic analysis of that, and then that's how one gets this particular first equality. And what we require in our case is some special cases of this result, wherein you get this 1 upon bq to the n plus 1 sub infinity written as some of these s infinite series. But I won't go into that. It's a simple thing, not a deep analysis, but it's nevertheless quite useful. Now let me come to another identity just on the previous page 26 of the last notebook. So Ramanujan has this, again, looks similar, but there is no parameter b, by the way. And there are 2 theta functions and 2 Rogers-Ramanujan functions. Again, Andrews proved in his monograph. And what he showed is that even in this case, even if you don't have b, specializing this appropriately gives you 2 identities which were proved by Watson involving the Rogers-Ramanujan functions. But using this identity and the identity of Ramanujan that we started our lecture with, we were able to get one more identity very easily. And this identity is one among the 40 identities that Ramanujan has given. These are not part of the original lost notebook that Andrews found in the Trinity College, but the manuscripts which came along with them and which are published in the Narosa. Okay, so these 40 identities were first analyzed by Brian Birch. There is a nice article by him titled A Look Back at Ramanujan's Notebooks, wherein he finds this list of 40 identities. And then since then, many people have proved, you can find the proofs of all 40 of them in this monograph by Berndt and his co-authors. They have tried to give arguments which could have been familiar to Ramanujan and not using maybe some advanced techniques. But nevertheless, they are quite ingenious. Like one needs a lot of ingenuity to prove such identities. Anyway, so this was one outcome of combining the two identities and appropriately specializing them. Again, here is that identity on page 27 that we started our lecture with. The important question is, how could one conceive such a relation? So it is well known that Ramanujan was a master of asymptotic analysis. And it is our speculation that he perhaps got at this relation or got a hint of this relation through asymptotic analysis. So let me try to convince. So let's start with the Rogers-Ramanujan identities. The Rogers-Ramanujan functions are actually equal to this nice Q products, both G and H. So before going to England, Ramanujan had already discovered these identities empirically, and although he could not prove them, he had several pieces of evidence. In fact, in the Lost Notebook on page 358 and 359, we see 4 pieces of evidence that Ramanujan gives for these identities. Later on, of course, he found proof by himself. Rogers found another proof of these identities, and Hardy arranged for their proofs to be put as a back-to-back papers in Proceedings of London Math Society, so that we all know. But before going to England, Ramanujan did discover these identities, although empirically. So how did he discover them? One of the pieces of evidence is he showed that both the left-hand side as well as the right-hand side are asymptotically equal to this exponential pi square by 15 times 1 minus q, as q tends to 1 minus. So let us try to look at this general theorem of Ramanujan, which is also given in page 359 of the Lost Notebook and is also in second notebook of Ramanujan. So if A, B, C, and Q are real numbers, A positive, B positive, mod Q less than 1, and Z denotes the positive root of A Z to the power 2B plus Z minus 1 equal to 0. Then as Q tends to 1 minus, this generalized Rogers-Ramanujan function is asymptotically equal to this particular right-hand side, where you have dilogarithm function now coming into picture. So this dilogarithm is defined for mod Z less than 1 by this infinite series, summation Z to the power n over n square. But one can also analytically continue, or one can write for any complex Z, this dilogarithm by means of this integral. Okay, so let us go with the result of Ramanujan. On the left-hand side, there was a sum of products, each product consisting of 2 infinite series. This was the product when S is equal to 2, which occurred on the first expression on the left-hand side, right? So we said that we do get this in more general case and answer the question of Ramanujan, because he has said for a general S, how does this behave as Q tends to 1 minus? And this is the answer that we found. How does one prove that? First of all, we should observe that there is no dilogarithm in here. It's only elementary functions. So why did this happen? So if we employ the result of Ramanujan, there was Bn square plus Cn, right? Put C equal to 0, put B as 1 by 2s. One gets this, which involves this dilogarithm. And Z1 is the positive root of this. I say the positive root because there is a unique positive root given the conditions a greater than 0, b greater than 0, and so on. Similarly, in the other sum, we are taking the product of these two, right? So in the other sum, we have s by 2, which is taken for b, and c is 0, and one gets this. And now when you multiply these two sides, here the exponential, the things inside the exponentials get added. But there is also one more important thing. See, there is this z1 here and there is z2. z1 is the root of this positive root, and z2 is the positive root of this. But there is a relation among z1 and z2. What is that relation? z1 is a to the minus s times z2 to the power s. Why is that the case? Well, just take this z1. Let's take this right-hand side and put it in here. For a positive s natural number, z2 positive, this is a positive quantity, right? So if I show that this also satisfies this equation, because of uniqueness, it must equal z1, because z1 is the positive root of this. And indeed, it is a trivial thing to verify that if you put this in place of this z, you will get the answer is equal to 0. Why? Because this is true. Okay? So that must mean that z1 equals this. So these two arguments in here, in the two dilogarithms, are related. And because of this identity, once you have proven this relation, either use this one or use this one to get that z1 plus z2 is equal to 1. So with this information, when we multiply the left-hand sides and accordingly the right-hand sides, you have this sum of dilogarithms, but there is a very nice functional equation for the dilogarithm. Li2 of z plus Li2 of 1 minus z is in terms of these elementary functions. And this is exactly the situation that we have. So with this, we actually see that the special functions, the dilogarithms, they vanish and leaving us, just logarithms in here. And those also simplify very much when you have this log of z1, log of z2, and this particular combination of the two. So you simply get log square a. And then for this thing, it's a routine simplification. So I won't go into that, but one can actually get the identity. Okay, so if I look at s is equal to 2 of this thing, which I just proved. So remember, this one we showed is asymptotically equal to this thing times exponential minus 1 by log cube times this, which simplified to just this pi square by 6 plus s over 2 log square. Now I'm putting s is equal to 2. So I get pi square by 6 plus log square a, right? That's what you see here. And when s is equal to 2, we already know that it is the first expression on the left-hand side of Ramanujan's identity. So this is what we get. Similarly, there is another expression, which is the second expression on the left-hand side of Ramanujan's identity, which can be asymptotically seen to be equal to this. Now, when we add the 2 to get the left-hand side of Ramanujan's identity, there is something magical that happens. When we add the 2, that is asymptotic to this particular thing. See, q is tending to 1. So when I put q is equal to 1 in here, you just get 4 plus a square minus a square root 4 plus a square, which is exactly the right-hand side, the denominator, sorry, which cancels out, leaving us this. Once, suppose Ramanujan has arrived at this relation, then it's a very easy thing for him to identify which expression will have this as its asymptotic formula when q tends to 1. Another expression. One of them is this, of course, that we have just shown, but which other thing, so that he can get the identity. Like for Rogers Ramanujan identities, he showed that the q product as well as g of q, both as q tends to 1 minus are asymptotically equal to exponential pi square by 15 1 minus q. Similarly, on this side, you have this series, the sum of the series, and he found it equal to this particular thing. Now, what else can have the same asymptotic? So that's pretty simple. If you look at this q product, 1 by q sub infinity, as q tends to 1 minus is this. And the theta function see these two things. The theta function has this, and when you multiply the two, these log q's cancel out, pi's cancel out. What you are left with, and what you see here is minus 1 by log q comes out, and pi square by 6 plus log square a. That's exactly what you have here. So you get exactly this thing when you multiply these right-hand sides. So what we have just shown is that this particular sum is equal to, I mean, asymptotically equal to 1 by q sub infinity times this theta function. Once Ramanujan has arrived at that by means of asymptotic analysis, he might have seen that, okay, it is not something that is true just for q tending to 1 minus, but rather it is true for all q such that mod q less than 1. And he may have gone ahead and proved this identity. So this is just our speculation. It may be a different thing also that he got this idea from. But that just explains a special case of Ramanujan's identity. Which special case? I mean, note that here everywhere you have q sub m or q sub n. There is no b. So once Ramanujan arrived at this relation, he had this exceptional ability to think that further one can put a b here to get bq. One can put a b to the power n in here, and then similarly a b in here, and then b to the power n here, and then you have a b in here, and then this particular sum, and then you can still get an identity, because that is what is given in page 27. Is there any explanation for this? We don't have it. We were able to get the explanation only for b equal to 1 case, because it comes through asymptotic analysis very naturally. But it's quite strange that he was able to conceive, if at all he went from a less general identity to a more general identity. If he has come first at this, I don't even know how he got there. Anyway, so this was just an analysis of how somebody could conceive such a relation, and we think it probably was through asymptotic analysis. Anyway, let me now move to the last part of my talk, concluding remarks. So Ramanujan wrote one paper. It's a one-page paper in Proceedings of London Math Society in the last year of his life, where he gives two algebraic relations between certain infinite products. And he says, and that those algebraic relations involve this h and g functions. And in that paper, he says each of these formulae is the simplest of a large class. So there are two formulas involving g and h. So what is the large class? It is believed to be the set of 40 identities that Brian Birch examined. What we think is that, of course, it could be that this itself is the large class that Ramanujan meant, the 40 identities. But because three of the identities involving G and H have these generalizations in terms of A and B, we feel by large class he's meaning this infinite class of identities pertaining to each such identity G and H, where there are A and B, two free parameters, and you specialize them and you get the identities between G and H. Again, this is a speculation. We don't know what exactly he meant when he said the large class. More probable is that the set of 40 identities itself is the large class. But because the three identities give us more general identities, I think there should be a search that should be made for other 37 or even more identities of this kind for G and H, which may have generalizations in terms of A and B. For now, after Ramanujan, none of the people have found any such A and B generalizations. In this work, what we have done is the already known generalization in terms of A and B has been generalized with a parameter S to get the dissection. But this remains to be done. So our main result shows that a theta function can be dissected as a sum of any number of products of generalized Rogers-Ramanujan function, because S can be any natural number. When S is equal to 2, we get Ramanujan's result. In that, when you put A equal to B equal to 1, you get the modular relation between G and H. When you put A and B both as -1, you get the relation between G and H and the fifth order Mach theta functions F0 and F1. Similarly, when we put S is equal to 1, we get a generalization of Jacobi triple product identity. And when A equal to B equal to 1, we get the Jacobi triple product identity itself. If you put A equal to B equal to -1, we get a relation between two third order Mach theta functions of Ramanujan. So you see there is one common thing in here. First thing is that whether S is 1 or 2, when you put A and B both as equal to 1, you are getting relations which lie in the theory of modular forms, because either you get a modular relation between G and H, like G of Q to the power 4 plus H of Q to the power 4, or you get Jacobi triple product identity. Of course, it lies in theory of modular forms. But when you put A and B equal to -1, you are always going into the Mach modular world, because you either get third order Mach theta functions or fifth order Mach theta functions. Now, somebody might say, what if we take S is equal to 3? Do we get seventh order Mach theta functions? So this is what we also were quite hopeful about. But unfortunately, it doesn't look like the series that are involved in there are related to anything like seventh order Mach theta functions. In fact, when you transcend this S is equal to 2 case, I don't think you lie. I mean, we go into even Mach modular world. It is something beyond the modular or Mach modular world. So let me try to explain this. How does one prove, or one empirically prove, Rogers identity? So let me take G of Q and divide it by this series and look at the asymptotic behavior as Q tends to 1 minus, using that result of Ramanujan involving dilogarithms. So if I just take the quotient, this is what I'm going to get, where U is √5 minus 1 upon 2. But there exists an identity for dilogarithms. This one, this exact thing in here becomes pi square by 24. So whenever you have something like exponential minus 1 by log Q times some rational multiple of pi square, that should be linked to a Q product. Because here you can see that minus Q square sub infinity, which is same as by Euler's theorem, 1 by Q square Q raised to 4 sub infinity, has exactly exponential minus pi square by 24 log Q. So asymptotically, we see that this has the same asymptotic as this. And then one can actually go ahead and prove it, right? And why I'm saying suddenly about Rogers identity, because we were thinking that for S greater than 2 also, we can have this sort of self-similarity, G of Q to the power 4. So let me try to give another argument saying why this is unlikely to hold for S greater than 2. Just take S is equal to 3 and A and B both to be equal to 1. Then our result gives us this particular expression. Now, the natural question, if you want to have self-similarity, is this Q series related to this? In the same way that G of Q was linked with that other sum in Rogers' first identity. So the answer, we think, is not true. I mean, we think that such a relation does not hold, as in, if we take the quotient of these two, it is very unlikely that this will be some Q product. Okay, why? So note that if you do the same asymptotic analysis of these two series, I take this, I apply the theorem of Ramanujan involving dilogarithms. Similarly, I take this, apply the theorem of Ramanujan, then take the quotient. This is the combination of dilogarithms that you get, where V is the positive root of ZQ plus Z minus 1 equal to 0. But now, is there any identity here linking Li2 of V and Li2 of 1 minus V, where V is this particular quantity, is the root of this cubic? The answer is there is one identity, and such identities can be found using Mathematica. Apparently, this was not given in any of the published works, or at least we could not find. But Jimmy McLaughlin actually showed us how to get such identities using Mathematica. In fact, he found this identity, but it can be proven easily using properties of dilogarithm. But nevertheless, even though you have Li2 of V and Li2 of 1 minus V, which is what are the functions involved in here, the combination here is such that when you apply it here, this side will still be dependent on this V. And as long as it is independent of V, there is a high chance that you can connect it with Q programmer. So because the V remains, even after the numbers in front are such that you don't get just a rational multiple of pi square here. You still are left with that one of the dilogarithms. And once that is the case, it is highly unlikely that the quotient of this will equal a Pochhammer. And so an analog of Rogers identity is unlikely. Okay, let me also say, okay, I have maybe 2-3 minutes. I'll finish off. So here is the second identity on page 26 that we also discussed. Can this identity be generalized like our main result? In that, this is also having n square by 4. So can we replace this 4 by 2s, just like we did it in our general theorem? Do there exist analogs of Ramanujan's result where one has sum of products of 3 or more generalized Rogers-Ramanujan functions? So like you have g of q to the power 4 plus q times h of q to the power 4, right? There are identities where you have 3 functions like g with different arguments or combination of those and sums of those functions. So for them, can we find a generalization of generalization of Ramanujan's result? That is one question that remains to be seen. So exactly, there are identities due to Sinai Robbins as well as Ranganath, as well as many other people who have worked on in this area of finding this modular relations between Rogers Ramanujan functions. You can have like 4 combinations of G or G and H, and then add it to 4 such other combinations, giving you some nice products or sum of products. So for them, what will be the corresponding generalization of Ramanujan's identity with A and B? That is another question. And this is the last slide. So if I put A equal to B equal to 1 in this series, which was one of the series occurring in our main results, and if I let K be between 0 and s minus 1, see, this is the K, then this series has occurred in a work of David Brassou, Jose Plinio O. Santos, and Paul Mondic, wherein they show 3 different restricted partition functions which have as their generating function this particular series with A equal to B equal to 1 and K between this. Not K in between this, because this is the general case, right? We also have in our result K between 0 to s minus 1. When K is less than or equal to s by 2, they have a partition theoretic interpretation for the coefficients of that generating function. The next question is that, what about the remaining cases? When K is higher than s over 2, but less than or equal to s minus 1, you have the corresponding series, put A equal to B equal to 1. It is also something which comes up in this nice result wherein you have connection with the theta functions and all. But is there any partition theoretic interpretation of that? Do there exist interesting restricted partitions functions coming out of that generating function? That remains to be seen. With that, I'll stop. Thank you.
Thank you, Atul. Any questions for the speaker?
Yes, I have maybe a question.
Hi,
Michael. Yeah, hi. There are some modular relations or equations of the Rogers-Ramanujan continued fraction, for instance, which involve base q and base q to the fifth, or other relations revolving base q and base q to the 11th. Do you have is there anything known to you which would be considered a Q-series extension of those relations?
It's a very interesting question.
That is
Yeah.
connected to your work?
So we did not touch upon the continued fractions aspect, but it's a very nice thing because you have G and Q coming out from this result of Ramanujan. In the special case, A and B both
Yeah.
equal to, this is G, this is H, and G upon H gives you R of Q, the Rogers-Ramanujan continued fraction. Maybe more generally, is this or some combination of that connected to a more general continued fraction? Yeah, that will be very interesting to see. But we did not look at continued fractions at all in our work.
Okay.
Yeah.
Okay, any other questions? Okay, if not, then let's thank the speaker.